Hello, I'm Ryan Baker, and today I'll be discussing 6 challenges for the future of artificial intelligence in education. Artificial intelligence has contributed a lot to education. Adaptive learning systems work. A meta-analysis by Kurt Van Lane suggests an average effect size of 0.76 sigma. And adaptive learning systems are now used at scale in a range of areas of education, and they're making a difference. This has led to a steady stream of discoveries and models in a range of once difficult areas to study, including collaborative learning, classroom participation and online connections, motivation and engagement, and metacognition and self-regulated learning. But we shouldn't rest on our laurels as a community. We can do much better. 0.76 sigma is only the beginning, and there are important challenges beyond just increasing overall effect sizes. And today, I'd like to discuss what I think are some of the key challenges. But first, I'd like to say a word about David Hilbert, mathematician, visionary, and wearer of spiffy hats. In 1900, Hilbert gave a talk at the International Congress of Mathematicians. And at this talk, he outlined some problems that he thought would be particularly important for mathematicians over the following years. This was one of the most eloquent scientific speeches of all time, and I encourage you to read it. Hilbert framed his problems concretely. He discussed what it would take to solve these problems and listed what would be necessary to demonstrate that the problems have been solved. They're hard problems. Only 10 out of the 23 have been solved as of right now. In the years since, there have been many lists of problems or grand challenges, including several in our field. And yet, few have been anywhere near as influential as Hilbert's problems. Most of them just list big, difficult, vague problems, which is very different than Hilbert. There are exceptions, the Turing test / Loebner Prize, the Millennium Prizes, but in general. Today, I'd like to suggest a list of problems to you. I know I'm no Hilbert, and I don't pretend I'm a Hilbert, but I do like spiffy hats, so perhaps I have something to say. And adaptive learning isn't mathematics. It's a very different kind of field. But I hope you'll give me a few more minutes of your time to discuss what I see as some of the bigger upcoming challenges in our field, not necessarily new to this talk, with a conscious attempt to emulate Hilbert by trying to frame specific problems with conditions for how we know we've made concrete progress towards solving them. The first of these problems is transferability, the learning system wall. The challenge is that learning systems learn so much about a student, but the next learning system starts from scratch. A student might use Dreambox one year, Mathia a couple years later, Alex a couple years after that. Each system learns a lot about the student, which is forgotten the second they move on. Or a student might use ST Math for some lessons and Khan Academy for others, like even in the same week. And each system has to discover the exact same thing about the student. This is a particularly big problem in our current era of COVID-19 online learning. It's like there's a wall between learning systems and no information can get in or out. If you seek better learning for students, tear down this wall, someone might have once said. It's not just a between system problem, it's even between lessons. A student's struggle or rapid success in one lesson usually doesn't influence estimation in later lessons. There's been some early progress. Eagle and colleagues have shown that there can be better student models if we transferred information between lessons within a student and a platform. But it was just a secondary data analysis on 3 lessons. So the contest is to take a student model developed using interaction data from one learning system, such as taking model inferences from a student, let's call her Maria, who's used that system. Take a second learning system developed by a different team and use System 1's model inference to change System 2's model inference for Maria and System 2's behavior for Maria. The change could be different content the student starts with, could be a different learning rate, could be a different interpretation of incorrect answers or other behavior. And within this contest, let's put a few conditions. The original model for the second system has to be a good model for that construct, with goodness metrics on held out data that are good enough to be published on their own in a respected conference or journal in the field. And then the new model for the second system has to be able to take an entirely new set of students and achieve better prediction than the original model. And the system behavior change has to be able to actually run in the 2 systems. In other words, the 2 systems have to actually be connected. This isn't just an analysis for the sake of publishing. Some initial progress. With Bruce McLaren and colleagues, we proposed technical requirements and an architecture designed to meet this challenge. Now, obviously, having the architecture plans isn't the same as having architecture, and having the architecture isn't the same as actually using it to transfer information from one system to another. But we hope that this will be a first step on this difficult path. The second challenge, effectiveness, differentiating interventions and changing lives. Today, we have many platforms that infer which students are at risk on the basis of learning analytics on student performance within a learning system, learning management system data, or other sources. They're used by instructors and other school personnel to make decisions about how to better support students, including selecting students for targeted interventions. There's some evidence that these systems lead to better outcomes for students, but there's also ongoing debate as to how substantial the effect is. And beyond that, are we really changing lives, or are we just patching short-term problems? The contest. Take a group of students. Randomly assign the students to a condition with the intervention or no intervention. Or, alternatively, establish equivalents for quasi-experiments where a model based on prior achievement and demographics cannot find significant differences between these two conditions. The condition can last up to, let's say, a year long. Then assign a learning analytics-based intervention, something based on a model, to a subset of students in condition E, where the model or criterion determines which students actually receive the intervention, and somewhere between 10 to 50% of the students in that condition actually receive it. So it's not something that almost no one receives, and it's not something that almost everybody receives, but somewhere in the middle. Importantly, publish or publicly declare the model or criterion from the start. Kind of like pre-registration, not quite. So identify in advance with documentation. You got an experimental condition, and you've got the model's decision. There's this group E star. The model thinks they should receive the intervention, and they are in the experimental condition. So in green, they receive the intervention. Nobody else gets it. There's a group that are in the experimental condition, but the model doesn't think they need the intervention, so they don't get it. There's a group, top right, that the model thinks they should get the intervention, but they're in the control condition, so they don't get it. And it's by comparing E star to C star and E star to E ampersand that we can really see if the intervention makes a difference. The contest is, at least 3 years after the intervention, collect a success outcome, such as standardized test score, attendance at graduate school, employment in the field, personal income, or something we never seem to study in this field, personal happiness, some actual real success outcome. Collect that and show that E star does statistically significantly better than C star. That is to say that the people who should have gotten the intervention in the experimental condition and did, do better than the people who should have gotten the intervention, but they're in the control condition, so they didn't. At the same time, demonstrate that E ampersand, the people who were in the experimental condition but didn't get an intervention, don't do any better than the people in the control condition who weren't supposed to get the intervention. Okay, third challenge, interpretability. Instructors speak Spanish, algorithms speak Swahili, chosen somewhat whimsically on the basis of 2 wonderful world languages. So we put a ton of effort into building models of important phenomena. We craft the perfect recurrent neural network, and we validate that it has brilliant predictive performance. It's a great model. And then the model, this wonderful model, makes a prediction that a user, an instructor say, finds non-intuitive. And we can't explain it to them. And the instructor, reasonably enough, doesn't trust it. And then they don't use it. The challenge is to make the decision-making processes of deep learning or a comparable advanced algorithm understandable for an instructor or other similar stakeholder, like an academic advisor, without a technical background. So the challenge? Build a model that predicts a learner's success outcome, like high school dropout or college course failure, or hitting below basic on a US standardized exam or the equivalent in another country, or failure in a training exercise, corporate training of some sort. And use an advanced algorithm, whatever that is this week, with at least 100 parameters. This model has to be a good model for that construct, with goodness metrics on held out data that are good enough to be published on their own in a respected conference or journal. And the contest, find 5 data scientists and 5 instructors who are not on the original development team. Design an explanation of how the algorithm works. Could be a visualization, could be a video, text, automated interactivity, those are all fine. Not a human to answer questions because that's hard to scale. And give each of these people 5 case studies or examples of specific students and ask them to tell you what decision the algorithm will make for each student and explain why. The contest, do the instructors agree with the data scientists at least 80% of the time in terms of both final decision and reasons for it, with acceptable inter-rater reliability, kappa over 0.6 for 2 independent researchers with a psychology background. Contest 4, applicability, knowledge tracing beyond the screen. So as a field, we have been reasonably successful at producing models that can infer learner knowledge or at least predict immediate correctness in computer-based learning environments. But mostly, these environments involve one student sitting at one computer and providing textual input, be it numbers, multiple choice responses, or so on. But most learning still doesn't take place with one student sitting at one computer. Even in the era of COVID, we still mostly have other types of learning. There's collaborative project work and team-based military training exercises and discussion forum-based learning and classrooms where teachers and students talk to each other, even if it's over Zoom. Can we detect student knowledge in these contexts as well? So the contest, take audio, visual, and physical data on learning from a setting where there's at least 4 students engaged in the same activity at the same time. Build a model that can infer at least 4 distinct skills or knowledge components for each student. And it's important to detect more than just overall proficiency. Then, for a sample of at least 60 students not used to train the model, this model must be able to predict immediate future performance on the skills with journal level quality. So imagine intelligent tutor system quality, knowledge recognition, and support in a live many student learning setting. Frankly, these days, I want to imagine a live many student learning setting, but that's just me in 2021. Yeah, could be kind of cool. Challenge 5, we got one more after this. 5 and 6. So 5, generalizability, the general purpose boredom detector. There's been success by several research groups in detecting academic emotion or affect solely from student interactions with the learning system, be it boredom or engaged concentration, or frustration or confusion, or even delight and joy. But the current models aren't generalizable. They have to be rebuilt almost from scratch for new learning platforms. There's some common tools out there for field observation, data synchronization, what have you. There's some experience in feature engineering that generalizes, but it's still a lot of work. Fiona Hollins and Ipak Bakir estimated that it costs about $75,000 to build these models. And furthermore, it's not clear what changes to a learning system cause these models to break down. My colleagues and I have seen that gaming the system models break down when you take the hints out of a learning system, but not when an affective agent is added. So the contest. Build a model of student boredom using interaction data from one or more learning systems. Apply this model to data from an entirely new system built by a different development team where the interaction is not broadly identical. In other words, not just a different topic or area in the same learning system. So for example, assessments to Mathia is okay. Apply a model with no tweaking or refitting or modifications. Features have to be defined the same way or in some way that's general across systems. In other words, it's okay to define something as 1 standard deviation slower than the mean speed in terms of each system's speed, because that's kind of generic, but it's not okay to say that we're gonna say it's 7 and we fit that, and now in this other system we fit it to 19. So the contest. Collect some ground truth, binary or categorical self-report, field observations, video coding with good inter-array reliability, doesn't really matter which one, and demonstrate that the model achieves acceptable quality in the new system. There's been some early progress on this. Luc Paquette basically did this, but for behavioral disengagement rather than affect, which turns out to be a lot easier, I guess. So he took an interaction-based detector of gaming system, he built it on cognitive tutor and Mathia data, and he validated it that it worked in assessments with no retraining, no mods. Kind of awesome. You know, hat tip shout out here. Then Stephen Hutt and his colleagues built an interaction-based detector of affect, and they built it for an algebra course in algebra nation, and then they validated it in a geometry course in algebra nation. So they showed that in the same platform, 2 different courses on different subject matter, you could build it and it would still work. So now all we have to do is take that next step, build a detector of affect and demonstrate that it works in a different learning platform with different designers. And I think that's going to be a little harder, but that's why this is challenge number 5. Challenge number 6, generalizability, the New York City and Marfa problem. Guess which is which? So models are mostly built on the samples that are already at hand, whether it's your current population of university students, the current user base of your adaptive learning system, or students who are relatively easy to survey or observe. But what happens when your population changes? Your university starts taking a lot of transfer students from Nevada. Your learning system is adopted in Alaska. A different branch of the military needs to use your training. You need to use your model for students just different than the ones you surveyed or observed. It's a challenge for inclusion. I call this the New York City and Marfa problem. It's hard to collect data and do research in New York City because of very restrictive rules. And it's hard to collect data and do research in Marfa, Texas, because it's 194 miles from El Paso International Airport, which is not exactly a huge airport itself. And we want our analytics to be just as valid for these students as for students who are easier to research, which is to say, suburban students and students in smaller cities that are have universities in them or companies that do this kind of tech. You could call it the Shanghai and rural Yunnan problem if you were in China. You could call it the Sao Paulo and rural Aracaju problem. Rural Sergipe. Showing my lack of knowledge of Brazilian geography here. One solution, collect data from all the populations you want the model to work on, and then try to validate your model on these populations, like in work by Jacqueline Ocampo and her colleagues. Both sensible and impractical. What are the populations? It might be more feasible to collect all the data in massive online open courses, MOOCs, than blended learning systems. But even in MOOCs, we don't know what the relevant populations are. We don't know, is it every country or what groups within which countries? We just don't know. So the challenge, develop a model that just works for new populations. Specifically, build a model of one of the following constructs: course or training exercise failure, affect, disengaged behavior, learning strategy. This model has to be a good model for that construct, with goodness metrics and held out data that are good enough to be published on their own in a respected conference or journal in the field. Then collect data for a population that's substantially different than the original population, where the data wasn't available when the original model was developed. So this can't just be an exercise of chop your data up real fine and find some transfer that works. You have to actually build the model, report the model, and then collect the data you're going to transfer it to. What do I mean by substantially different? Let's come up with an operational definition. Let's say that the population is more than 50% belonging to a group that was under 10% present in the original training set, where the group differs from the original training set in terms of perhaps degree of urbanicity, rural versus non-rural, race, nationally recognized census category, ethnic group in a nationally recognized census category, native language, nationality or citizenship, or poverty using a nationally appropriate and common category. The prediction for the new population has to have only minor degradation in performance and remain better than chance. There's been some early progress on this one, I'm pleased to say. Lopez Zambrano and his colleagues at the University of Cordoba in Spain took prediction models of university course failure. They demonstrated that models can generalize to courses in unseen academic subjects, totally new academic subjects, using the BLAP6 criteria. These criteria. The academic subjects in this case had fairly different student populations, but they didn't explicitly document the difference between those populations according to the BLAP6 criteria. So womp, womp, womp. We don't have a winner yet, but this is pretty good progress. So to reprise these challenges, six challenges. The first one, transferability, the learning system wall. Can we build a way for learning systems to share information about students that's meaningful? Second one, effectiveness, differentiating interventions and changing lives. Can we demonstrate that a learning analytics-based intervention makes a difference for the students who get it, but doesn't make a difference for the students who don't? Interpretability, instructors speak Spanish, algorithms speak Swahili. Can we build an explanation of some sort of a complex algorithm that everyday users understand the same as data scientists? 4, applicability, knowledge tracing beyond the screen. Can we develop good quality knowledge tracing on activities that aren't just one student, one computer? 5, generalizability, the general purpose boredom detector. Can we build a model that detects student boredom and transfers between learning systems? And finally, generalizability, the New York City and Marfa problem. Can we build a model that just works for totally new segments of the population? So these, I think, are some big, hairy, difficult problems. And so I'd like to give you an incentive for solving these challenges. I'd like to announce a prize that will go to the teams that are first to solve each of these challenges. Announcing the Baker Learning Analytics prizes, BLAP, with an award of, drum roll please. It's way less impressive when you do it on your own desk. Please, I hope you drummed along. With an award of $1. $1. Actually, $8 because I've gotten matching funds of $7 and I believe in those people when they say they're gonna come through. So, concluding thoughts. In this talk, I've proposed a few challenges that I think would bring our field forward and some conditions under which we would know there's been progress. I hope you found these challenges compelling, or at least thought-provoking. Ultimately, a field moves forward if it takes on big goals that make a difference. One of the things we have to watch out for is becoming obsessed with tiny optimizations on small problems. What I've presented today might not be the right big goals, but at minimum, I hope I've provoked you to think about what the right big goals would then be. Perhaps even write your own competing challenges like Radek Pelenik did. His challenges are very different in kind to mine, and I encourage you to take a look at his too. So follow the progress. I have a webpage up which has the progress on each of these challenges. Today's talk is current as of the day you're seeing it, if you're watching it like at the official conference workshop slot. But either way, feel free to follow this webpage next week, next year. Hopefully we'll see more progress. There's been progress this year, so I have a lot of hope. Thank you very much. Final commercial. If you are interested in reading more about our work, we have a massive online open course, Big Data in Education. All of our lab publications are available online. Google Ryan Baker, not the footballer. And we have a Twitter and a Facebook feed that have all of our newest scientific results. So thank you very much. And I've probably already been taking questions in real time while you've been watching this, but I'm happy to take more questions. Thank you very much. Have a good day.